We introduced proximal persistence, a geometric approach for spatial hand-based interactions for a 3D shape modeling metaphor inspired by pottery. Proximal persistence is a cause-effect model, which allows users to progressively guide the shaping of a virtual object through the shape of their own hands. The idea is to define the modeling process of a 3D shape as a time series of its deformed states, converging so as to conform to a point-sampled manipulating object. Our modeling technique is inspired by the well-known exponential smoothing technique, which is used for smoothing time series data. We use this technique to formalize the notion of persistence, wherein a portion of the modifiable shape is gradually attracted towards a modifying object. In this simple 2D example, consider a shape and a point defined as a manipulator. We first compute the handle, which is the point on this shape closest to the manipulator. We displace the handle towards the manipulator by a fraction of the distance between them. We call this fraction the persistence parameter. Using this displacement, we can initialize a C displacement profile in a specified neighborhood of the handle. We compute a smooth deformation of the shape by selective application of the Laplace operator on the C displacement profile. A pot is represented as a single homogeneous generalized cylinder consisting of a vertical stack of circular sections. Given the point cloud, we compute a gradually displaced handle, thus modifying the profile based on the value of the persistence parameter. If a section contains more than one handle, we select the one closest to its manipulator. The deformation of the pot is achieved by rescaling the sections so as to fit them according to the deformed profile. We can broadly classify a potter's intent into pull and push, that is, outward and inward deformations. In this example of a push, notice the contact between the hand and the pot. When pulling, notice the gap between the fingers. We use this information by allowing for outward deformations only in local neighborhoods, around inward deformation when required. This is in contrast to the existing approaches that use finite hand gestures to rigidly designate such intent in a symbolic manner. Our pottery application is capable of getting user inputs from two diverse depth sensors. The general modeling pipeline comprises of the user, a depth sensing module, the computational module, and a visual feedback module. We designed an interface comprised of a scene with a rotating pottery wheel and a natural outdoor background. The first example shows our application using the close-range RGBD sensor, which can be used to obtain live streams of point clouds of hands or tools to define a manipulating object. Users can directly shape pots using their hands similar to how they would interact with a real lump of clay thrown on a potter's wheel. Note that both our technique and the pottery application are three-dimensional in terms of geometric representation and handle displacement. The user can approach the pot from any direction. Potters frequently improvise by using physical objects as tools to give distinct shapes or pots. Our users can do the same using our application. In the following examples, we demonstrate our approach with point clouds extracted from skeletal and boundary images of the hand. The second example shows our application using the leap motion controller. Leap motion is a depth sensor which provides a skeletal representation of the hand comprised of the palm and fingers. We use this device to implement a wide range of virtual tools. Each tool is defined by a prescribed set of manipulators, that is, predefined point clouds. For robust and unambiguous tool selection, we partition the 3D scene into three distinct interaction spaces, which map to the interaction space of the leap motion controller. The user can freely transition between the spatial partitions by simply moving towards the right or left extremities of the leap motion device. When selected, the motion of the tool is mapped to the user's palm position. In this paper, we demonstrated the augmentation of users' existing knowledge of the real-world manipulations with new virtual modeling contexts. To the best of our knowledge, no existing hand-based spatial modeling scheme offers such diverse contexts of user input, including the use of everyday real objects as tools for virtual shaping. Thanks for watching.